So, fast forward a few years, and I was in high school, and I used to, stay home from school sometimes. You know, I was, sick for the day, and I would spend the time actually trying to teach myself how to program because that was something I got excited about. I was exposed to computers when they were sort of a brand new thing, and I spent the summer working doing like landscaping work so I could save up and get a personal home computer. It was a Commodore 64. And in order to get it to do what I wanted it to do, I had to teach myself machine language programming, which is programming at the level that the computer thinks, kind of in ones and zeros, because using the regular programming languages back then was just too slow. Oh, I've got someone who knows what a Trash 80, sorry, I mean TRS 80 Model 3 is. So, we used to joke around with our own nicknames for these. So I'm in good company here. So I taught myself so I could program this game Defender on my computer and save myself the quarters down at the arcade. But really, it was more just to see if I could do it. And I was really surprised when it actually worked. So then that was a big encouragement to me. Looking back, if it hadn't worked, maybe I would have gone in a totally different direction. Probably not. So. I realized, that there's this sense of amazing power to be able to take a machine, tell it exactly what to do, and have it follow those instructions. And I thought, wow, you could use this in so many cool ways. But at the same time, I was kind of an adolescent experiencing that angst that goes along with being that age. And I was fascinated by human psychology and trying to figure out the meaning of life and those kinds of things. So I didn't really want to pigeonhole myself into becoming like a computer engineer, but I didn't want to let go of that. And fortunately, I discovered this field called cognitive science, which combined those two areas of interest. And I enrolled at the University of Rochester and pursued this so I could learn about artificial intelligence and psychology and neuroscience. And it was basically about trying to better understand how thinking happens, whether it's in machines or natural thinking systems like humans or other animals. And then what could we learn from how humans think and apply that to machines? And how could we use machines to model the way humans think as a way to better understand how that works? So it's really fun, cool stuff. And then around that time was when the internet kind of started to become more popular. People were using email a lot. This was pre-web, or the very early days of the web. So there wasn't a lot of web browsing, but it was very present for me because I was working with these neural network models where we would try to create computerized models of the brain and model each neuron and how they were connected to each other and how information would flow across these. And very present for me was this metaphor to the internet where we're all sort of nodes connected to each other in the internet. And I thought, oh, it's kind of like people are neurons in this big global brain. But I wondered, could that be more than just a fanciful metaphor? Could that actually be a model for thinking collectively? Could we somehow put some structure on that and create a kind of a global brain and do some useful things with that? And I think part of what fascinated me as I started to explore this duality of human and machine-based thinking is in the different ways in which humans and machines think. So when I would go and tell my home computer, hey, do this step, then do this, it would always do it exactly the same way every single time. Well, humans don't tend to be reliable in this way. We're not good at remembering things. We're not good at symbolic reasoning. You could take a dollar store calculator and do arithmetic on there faster than any human could do arithmetic because machines and humans just think in fundamentally different ways. They sort of complement each other. So the idea was, could we figure out ways to build systems that combine humans and machines and play to these complementary strengths? One of the things that you hear a lot about today is artificial intelligence, and one of the holy grails of artificial intelligence is to create human-like thinking in a machine. And the perspective that I come from to this field is that we already have the capability of human-like thinking, and it happens to be called humans. So why don't we use those humans in combination with the things that machines do well in order to achieve futuristic AI capabilities today. I had an opportunity to put some of these kind of lofty ideas to a really practical application when I met Chris Schaefer and Nozomi Nishimura at Cornell University's Department of Biomedical Engineering. So they're studying Alzheimer's disease, and they had this problem where they had these huge amounts of data associated with each research question that they ask about Alzheimer's disease. And it would take 6 months to a year to analyze the data from those questions in the lab by trained lab technicians. And so the premise of their work is that since almost the beginning of Alzheimer's disease, we've known that Alzheimer's patients have about 30% less brain blood flow than healthy people, but we hadn't understood the mechanism underlying that. So why do we actually see that in Alzheimer's patients? And so that was kind of the basis of their work, and they figured out through some studies involving mouse models of Alzheimer's disease. That's where you take a mouse and you give it the human gene for Alzheimer's disease, and that mouse actually develops the physiological symptoms of the disease and the cognitive symptoms associated with the disease. And they developed a method to look into the brains of these mice while they're alive and see the blood flow in the brain and where it's getting kind of impacted potentially by the disease. And what they found is that that it was these tiny capillaries in the brain that were getting clogged, and that the downstream effects of these blocked capillaries was causing a 30% reduction in brain blood flow in the mice, just as we were seeing in human patients. So they gave these mice a chemical compound that released these stalls, and it restored the blood flow, and the mice got their memories back, and their cognitive symptoms went away almost instantly within hours of this. So this was, a really kind of mind-blowing finding for me, and very compelling for me to want to try to help them solve this problem of analyzing the data. So, it's a very slow pace of progress if you're only answering research questions every 6 to 12 months. And one of the things that we can do with citizen science is we can bring to bear the cognitive abilities of the general public to tackle massive data problems. The idea is that instead of having 2 or 3 trained technicians in a lab trying to solve a problem and analyze all these data, what if we could create an online game, which we did, that many people could play, and with everyone contributing, we could analyze the data much faster. So that's what we did. We created Stall Catchers, and we have almost 30,000 people who are registered on Stall Catchers today and helping to analyze the data 5 times faster than it's analyzed in the lab. On any given day, you might find 50 to 100 of those people playing the game, some days more, some less. And we're answering research questions now every 1 or 2 months instead of every 6 to 12 months. Since the project started 4 years ago, we've been able to not only answer research questions, but share those results with the scientific community. And we, if you can see my little arrow here, we acknowledge the Stall Catchers players as contributors. And this is a hyperlink when we do this. So if you click on it, if you go to the website of the academic journal and click on Stall Catchers contributors, then you actually see a list of all the people who specifically contributed to answering that research question by playing Stall Catchers. So we think this is, important to recognize how folks are contributing. The other thing to show here, so this is kind of a complex looking diagram. This is a fancy hypothesis. This is kind of a diagram that shows what the Schaefer-Nishimura lab thinks is happening inside the brain to cause the formation of these stalls that are blocking blood flow. And these are what they would call molecular mechanisms. So, what's actually happening at a biochemical level in the brain to cause that. And each check mark here is one question related to this model that's been answered by Stall Catchers. And so far, all the answers are consistent with this model. And then the question marks remaining are the remaining questions to be asked to sort of to provide strong evidence that this is a correct model. With that model verified by Stall Catchers, then we have a really good basis for exploring treatment targets based on this approach. which could make a real world difference for people living with Alzheimer's or people who might someday get Alzheimer's and maybe even be able to prevent Alzheimer's. So I'll just give you a quick peek at what Stall Catchers looks like. So in this video, you can see there's this kind of orange outline here, and that's showing the person who's playing the game a specific capillary in a mouse brain. And then when you're playing the game, you just have to say whether you think blood is flowing through that capillary or not, whether it's flowing or stalled. And there's a mini tutorial that kind of walks you through the process of, some examples of what it looks like when it's flowing, what it looks like when it's not, and how to play the game. It's a pretty simple game, to be honest. Well, I should say easy to learn, hard to master. So I would say I'm a very mediocre player. I only get, maybe 70% of them right. But the cool thing about Stall Catchers is that we use a technique called wisdom of crowds to combine answers from many different people. So the one time or the two or the three times you get it wrong, someone else is getting it right and your answers are getting combined. So there's not all this pressure on one person. We've actually set it up so no individual person can mess up the research. So Great. I'll stop there.
I actually